Hello again. This is a geometry video, and this is about the first section in chapter 2. We're starting to get into different kinds of reasoning in this chapter, and the first section is about inductive reasoning. So basically what inductive reasoning means is we either build a pattern and try to make a conjecture, or we examine a pattern and try to make a conjecture. Now a conjecture is a statement you believe to be true based on inductive reasoning. And again, inductive reasoning is examining or building a pattern following some kind of rule. And that rule is often called our conjecture. Alright, let's do it. 2, 4, 6, 8, 10. If I were going to continue this, I'm saying we're going 12, 14, 16, 18, forever. And my conjecture is that we are listing, alright, let's move to the next one, 3, 6, 9, 12. If I continued, I would say 15, 18, 21, 24, 27, 30. And my conjecture is that we are listing, now certainly we could phrase these in other ways. I could have said positive multiples of 2 for this first pattern. This pattern, Monday, Wednesday, Friday, Sunday. Well, it looks like we're skipping Tuesday, and then go to Wednesday, skip Thursday, go to Friday, skip Saturday. So my guess would be after Sunday, we're going to go Tuesday, skip Wednesday, Thursday, skip Friday, Saturday, skip Sunday, and then we're back to the beginning. So I might say my conjecture is, in this pattern, we have triangle, quadrilateral, pentagon, hexagon, octagon. My conjecture is we're going to increase the number of sides by 1 each time. For this page, I'm going to attempt to complete the conjecture to make it true with something we've used a little bit in class, which is sometimes, always, or never. And then when I'm finished, I'm going to double check my conjecture by searching my brain for a counterexample. A counterexample would disprove a conjecture. And hopefully we'll find a few counterexamples to demonstrate how that works. So let's see if I can fill this one in. The sum of two odd numbers is sometimes, always, or never odd. Well, let me see if I can build a little pattern here. Use some inductive reasoning. Odd numbers. And the sum is addition. So those are both odd. And I get an even. The sum of two odd numbers. 3 plus 5 is 8. That's even. 5 plus 7 is 12. That's even. 7 plus 9 is 16. So my conjecture is going to say that the sum of two odd numbers is never odd. And you can maybe be thinking along with me here. Is there any counterexample where I could actually find two odd numbers, add them together, and get an odd number? That would make my answer sometimes. I can't think of one, so I'm going to move on to the next. The product of two numbers is sometimes, always, or never odd. Well, let's try this. 1 times 3 is 3. That's odd. 1 times anything is itself, so let me skip to 3 times 5, and that gives me 15. Okay, how about 5 times 7? 35. 7 times 9, 63. So far, every product of two odds is giving me another odd. 11 times 3, 33. So my conjecture is the product of two odd numbers is always odd. And I'm going to tend to believe that this is true until I find a counterexample. Alright, once again, prime numbers are always, sometimes, or never odd. Well, let's list some prime numbers. What are some prime numbers? 11, 13, 15 is composite, 17 is prime, 19 is prime, 23 is prime. So my conjecture is that prime numbers are always odd. And now there's some smart person out there who is immediately thinking of a counterexample. So my counterexample for this conjecture is the number 2. It is prime, and it's also even. So what we just did is we just proved this conjecture to be false. So if we are going to do any proving, it will be to prove a conjecture false with a counterexample. Now let's look at a few problems from your book. This could be helpful for homework in section 1. Number 20, the instructions say make a conjecture about each pattern. Write the next 2 items. Well, it's looking to me like some multiplication. 2 times itself is 4. 4 times itself is 16. So my conjecture is each term squared is the next term, or times itself. So if I square 16, my next term would be 256. If I were to square 256, my next term would be 65,536. All right, number 21. 1/2, 1/4, 1/8. Looks again like a multiplication sequence. If I multiply this times a half, I get 1/4. Multiply by a half, I get 1/8. So my conjecture is that I'm going to multiply. So let's multiply 1/8 times 1/2, and that gives me 1/16. Times a half is 1 out of 32. All right, number 22. 3, 6, 9, 12. Looks like multiples of 3, but we're changing signs, so I'm just going to describe that. And so my next term would be 15, which would be negative, because my previous term was positive, and then positive 18. Okay, now page 77 at the very bottom, number 23. This problem was very confusing, so what I did was I sort of rearranged it and changed the instructions a little bit to help you see what was being asked. So let's first look at these patterns here, and what we have are square numbers. This is 1 times 1. This is 2 times 2. 3 times 3. 4 times 4. 5 times 5. Right? This is consecutive square numbers. Each has a square root, which would be the dimension of these perfect square arrays of points. So what is being asked is, from here to here, how many points did I have to add to get the next square number? And so what I'm going to do here is just find the difference, 3. And then from this square number to this square number, how many points did I have to add to 4 to get 9? And so another way to describe it is 9 minus 4 gives me 5. And then how many points added to this 9 gives me 16? So the difference is 7. And then from 16 to 25 is 9. So what's being asked is, for any n value, what was the amount added? So when n is 1, when we're going from 1 to 4, we had our first difference of 3. When n is 2, so this is our second number we're looking at from 4 to 9, the difference was 5. When n was 3, we got 7. 4 gave us 9. And so let's see if we can make a conjecture here. 5 gives me, it looks like we're going 3, 5, 7, 9. Right? Consecutive odd numbers, it looks like. So when n is 6, that gives me 13. Now when we talk about a rule, it depends on the kind of pattern we have. This particular pattern, what we're doing here is, let's look at differences again. We're adding 2 to get the next term. 2, 2, 2, 2, 2. That's the difference between 5 and 3, between 7 and 5, and so on. So what we call this is letter D, which is our common difference. That's a C. Common difference. N is, which term am I looking at? My first term, my second term, my third term, my fourth term. And then when I use the letter T, this is referring to a term. So T sub 1 is 3. T sub 2, T sub 1 is 3. T sub 2 is 5. So what we would get here would be T sub n. And I'm looking for a rule, whoops, that's an n, that given any term number, I can find that term. And what we're doing here is we're going ahead to pre-calculus to steal this formula. And here it is. those of you interested in advanced math, you might want to write this down. If it's arithmetic, arithmetic means that there's a common difference between terms. That common difference will be this D. This is our term number. This is our first term. And this is the term in question. And what we get here, this whole expression of the first term added with n minus 1 times the common difference, is our rule. So this is like a formula for finding any term you want in an arithmetic sequence. So let's find the rule. Let's remember that for t sub n, our first term was between 1 and 4, 3, n minus 1, and then when we went through and found 3, 5, 7, 9, 11, this common difference was 2 between the amount needed to add to get the next square number. So our common difference is 2. And this was our t sub 1, our first term. And so our rule will be to get any term number we want, let's distribute the 2, 2n minus 2. And now let's combine like terms. T sub n will be 2n plus 1. And that is the answer to number 23. Kind of a complicated problem. Okay, let's turn the page. 78. Instructions say, determine if each conjecture is true. If not, write or draw a counterexample. So let's look. Points x, y, and z are coplanar. Well, I'm going to say this is true, and my evidence is we have a postulate from chapter 1. Any 3 points determine a plane. And I think we'll be hard pressed to find a counterexample. So I'm pretty confident this one is true. Number 25. If n is an integer, then the opposite of n is positive. Well, let's see. Let's let n equal negative 10. That's an integer. The opposite of negative 10 is what this would be explaining. The opposite of n, since n is negative 10, the opposite of negative 10 is 10. So far, this conjecture is looking true. But let's let n equal a positive integer, positive 6. The opposite of 6 is negative 6, which has proven this to be false. So 6 was our counterexample. Number 26. In a triangle with one right angle, 2 of the sides are congruent. Well, certainly I could sketch a right triangle, pretend that's a nice right triangle, and I could say that the legs are congruent, and this would be true. But there's nothing that tells me that I could not have a scalene, and I think the most famous scalene right triangle is a 3, 4, 5. And we could prove it with the Pythagorean theorem. So this is my counterexample to prove this conjecture as false. Number 27 says, if ray BD bisects angle ABC, so let's do a little sketch of this. So here's angle ABC, ray BD, I'll try my best to sketch this to make it look accurate. If this bisects, that means we get congruent halves. And so this equaling this, ABD equals CBD, I'm saying this is true. I can't think of a way where this could be proven false given, and when we get to two-column proofs, this explanation right here we'll use quite a bit. The definition of bisectors, definitions of midpoints, etc.